Today we're going to be talking about logarithmic functions. So logarithmic functions actually are very closely related to what we talked about in the last section on exponential functions. And the relation, if you remember, we were talking about these things called inverse functions at the end of the previous test 3 material. And so it turns out that an exponential function and a logarithmic function are inverses of one another. And we'll talk about more of what that means as we go on throughout the section. So mainly I'm just going to start off by talking about a bunch of factoids about logarithmic functions. So these are all things you need to know throughout this section. So you'll notice all this on the first page of the notes for this section. So this is all stuff you need to keep in mind. And so we'll just start off with a logarithmic function by definition. So a logarithmic function, normally it's just log. So if you were to type in log-based solutions in MyMathLab, you would type in log, just straight off of the keyboard. And so this is a subscript. This is also, well, this is something that you can find on the palettes at the very bottom, and one of them is subscript. You can also press, I think, Shift hyphen, and you can get the subscript notation. You will be doing that quite a few times. This subscript though, this A here, it's a little bit tinier than the other stuff around it. And that's because this is called the base. So this would be log base A, or with base A of X. So that's how you would read this, log base A of X. And so that's, whenever you see that, that's called a logarithmic function. Now, in addition, there's something called a natural log. And a natural log, you'll see this quite a few times in the homework. It's a special type of logarithm. It's so special, in fact, that they gave it its own name. And so if there's any problems that say express your answer as a natural log, they want you to use this. So this is ln. So if you were to type this in MyMathLab, you would legitimately type in ln. And how this is related to log, so I said the natural log is a special type of logarithm. So this is when the base is the number e, which we talked about in the previous section, Euler's number. So if you have log base e of x, you can swap out that notation simply for ln. And this is the only special case of this. We'll see more examples that kind of utilize this idea, but there's a logarithmic function that looks like this, and a natural log, which is a special type of logarithm. So everything I'm going to talk about with respect to logarithms, natural logarithms follow the same exact series of, well, the same outline, ultimately. And so we move on. So again, I'm adding another parent function, another function to the library of functions in the shape of this one. So before we had an exponential function, which had the shape like this, but one of the consequences of the inverse relation between exponentials and logarithmic functions is that they are symmetric with respect to a diagonal line. Now, if you want to think about it that way or not, you can do so, but virtually the difference between exponential and logarithmic is that all the x's and y's completely swap. That's what it means to be an inverse, or the scope at which we look at it. So everything about exponentials swaps. So before, exponential had a horizontal asymptote at y equals 0, but since x's and y's swap, that horizontal asymptote becomes x equals 0. And notice I have that written down here. Before, the domain of exponential functions was all real numbers. Notice that switches to the range here, because inverses mean you swap x and y. And additionally, the range of exponential functions was 0 to infinity for the standard parent function. And notice that's what's now here as the domain. So everything switches. So this is another function that you need to add to your library of functions. This is definitely one you need to know offhand. And finally, we have this association between exponential functions. So we know it's an exponential function because, well, there's an exponent. And this is a logarithmic function because there's a logarithm. And what this special notation means is that these two mean the exact same thing. If you have this form, you can rewrite it like this. And if you have this form, you can rewrite it like this. And we're going to find out throughout this section that both of these forms have a lot of utility to them. We want to actually start off this section by determining how to swap between both of these and see how this will help us solve problems algebraically. So we start off with looking at a problem that involves changing exponential statements to logarithmic statements. So we have two separate problems here, as you'll see in the notes. And the goal is they want us to just simply rewrite these involving logarithms. So by the time we conclude with the problem, we better have a logarithm present. Now I went ahead and rewrote the rule that was on the far right over here just a second ago. And this is precisely what we're going to utilize. This tells us how all these components will shift. For example, the a here becomes the base of the logarithm. The exponent becomes, well, what the logarithm equals, and x here ends up being trapped within the logarithm. So things shift a little bit. So that's something to keep in mind. So it's not simply just a here, y there, and x there. It doesn't translate as equivalently as you would expect. So make sure you're aware of how everything's associated. So over here, if we follow the rule, so if you want this statement over here, so we want this statement to match this one as closely as possible. This statement has the exponent part on the left side. Here, the exponent's on the right. And if you want to, you can just simply swap the sides. You can simply swap the sides because, well, that will match up with the starting statement over here. So we haven't solved the question yet. We simply match this part up here. So now we see that 4 is a, the 2 here is y, and 16 is x. So if we want to rewrite this as a logarithm, well, it says whatever the a was, make that your base of your logarithm. So let's go ahead and do that. So we're converting a form like this to a form like this. That's what the problem's asking us to do. And so it says, start off by putting a log. And so it says your base for your log is the base of your exponential. Remember, the base of an exponential is whatever has a power raised to it. So it says 4 here, make that your subscript. Notice I made it tiny and I inverted it downwards a little bit. That's a distinction that you have to make when you input these answers into my math lab. So that's the first part. And then from here, it says x here will go next. The x is what the whole exponent is equal to. So the whole exponent is equal to 16. That tells us exactly to put 16 here. And then it says set that equal to y, where y ends up being the exponent itself. So the exponent is 2. And so this is actually it. This is our answer. This is all it wants. It just wants you to be comfortable with rewriting exponential forms as logarithmic forms using this conversion formula. That's all this is, a conversion formula. So let's look at another one over here. So this one has that e thing again. Remember, that's an important symbol. It means Euler's number. We have a special interest in that, and you'll see what I mean momentarily. So it's already in the form that matches here. The exponential part's on the left-hand side. So here the base ends up being the base of the logarithm. So now we have log base e. The base of the exponent becomes the base of the log. And then from here, it says what the whole exponential function is equal to. That's what is now in the logarithm. So here, this whole thing's equal to 14. So that tells us the 14 goes right here. And we set that equal to y, which is the exponent. The exponent here is x. And so notice, and again, just like with this problem, this would be our answer. Additionally, you might notice log base e, remember that's how you would read this, log base e. We just mentioned a moment ago that there's a special symbol for this. That symbol is ln. So remember, we just mentioned the natural log from the very beginning of this lecture. You can put an ln anytime you see a log base e. My math lab will accept both answers. I like to put parentheses here, and you're more than welcome to put parentheses around whatever the log is applying towards. But ultimately, these conversions, as well as these associations, will be, we'll address these more throughout the section. So now we're going to look at two problems that are fairly similar to the previous problem, except we're going to be going in the opposite direction. So instead of converting exponential functions to logarithmic functions, so instead of going this direction, we're going the converse direction. We start off with logs, we want to end up with exponents. Both directions are very helpful as we go through these problems, as you'll see throughout the section. Go ahead and start with this one over here. So what you could do is make sure that your logarithmic function matches the form over here, and you can go ahead and match everything accordingly. What I'm going to show you is a method I've seen high school students use, and I think it's a good mnemonic way of remembering how everything's organized. And it's loosely referred to as the windmill idea, And what you do, so if you want to rewrite a logarithm as an exponent, you can circle the base. So the base of this logarithm is 9, it's the tiny number, and you wrap it around. You wrap it around just like this. So people call it a windmill or an arc, whatever you may want to call it. And this right here actually tells you how to organize all of your numbers to go from a logarithm to an exponential. So let me demonstrate that. So the number we started with is 9. So we go ahead and jot down the 9. The exponent of 9 is going to be 3. And what is that all equal to? Well, the arrow is pointing to what the whole exponential function or expression will be equal to, 729. This would actually be our answer. Additionally, you may, it's perfectly sufficient for you to just memorize that the base of the log is the base of the exponent. The number over here is your exponent here, and x carries over as such. Or you can also use a mnemonic way of remembering it, such as this one. And I'll demonstrate it for the next problem as well. But just for this problem, it only wants the conversion. It doesn't want you to do anything more. So we'll go ahead and look at this problem right here. And if we try to consider the same option, so notice there's an ln, that's the fancy logarithm. So the problem is, well, natural logs do not have a subscript. They do not have, well, at least a visible base from what we're looking at. Aesthetically, there's no base. So if we start to try and use that windmill loop process, there's nothing to circle. So you might think, well, what do we do in this situation? And what we end up doing is making the observation of, well, ln of a number, that's the same thing as log base e. Remember, we said this at the very beginning. ln is the same thing as log base e. So if you can make that observation, now we do have a subscript. Now we do have a base that we can go ahead and circle. We can loop around, just like that. And this tells us exactly how to organize all the numbers and or variables to go from a logarithmic function to an exponential function, just like we did in the previous problem. So we start off with the number circled, that's e. Since this is an exponential, we need to know what the power is. That's e raised to the x. So this curve tells us the order in which things are organized. And what's all of this equal to? Well, that's what the arrow points to, 11. And again, it just wants the statement. It even says type an equation in your homework. So that would be sufficient for this problem. So now what we're going to look at is evaluating logarithms using a calculator. And the way these problems are constructed, they end up saying not using a calculator, but in the past I've just shown students how to use it because I think it's a more helpful utility. So I'll show both methods and you can choose either one, but I think the calculator way is a lot more efficient and helpful. So I did provide a formula here, and I consider this the calculator-friendly interpretation of logarithms. So if you have some standard logarithm, you know, the ones that we've been dealing with thus far, so the calculator-friendly version of this, because a is a subscript, and there's no subscript in the calculator. So actually the calculator, if you notice, if you look on the first column, the second button, you'll see log right on there. And that's what we're going to be utilizing. Right underneath it is ln. That'll come up as well. But log and ln, first columns, second and third buttons respectively, that's what we're going to be utilizing. And so if you were to play around with the logarithm button, you will notice that it does not give you the option for a subscript. It does not have a way for you to put the a value in. So instead, you have to use this calculator-friendly version that gets rid of all the subscripts. So it starts off, and the order is important. It's log of the number you're evaluating on top, divided by log of whatever your base is, whatever the subscript is. And this order is very important. You have to put it log of this number divided by log of your base, in that order. So let's go ahead and look at that for this initial problem here. So if we follow that exact formula, that tells us that we start off with log of 1, because log of the number that is being evaluated, divided by log of 3. And so if you put all of this directly in your calculator, you put log of 1, you close parentheses, divide that by log of 3, you close that parentheses. If you do everything correctly, what you should get is actually 0. So you would end up getting 0 for this problem, and that would be correct here. So that's the calculator way of doing this. I also mentioned that there is another way of doing this problem, the non-calculator way. So if you prefer to do it this way, so what you do is suppose all of this is equal to y. And so y is what we're trying to figure out here. And so we would apply that same loop method that we talked about before. We would need to rewrite this as an exponential function so we can make sense of this. We're not really too familiar with logarithms quite yet. That's why I'm introducing all of these shortcuts for the time being. but we would use the lineal method as we used before, and that tells us exactly how to rewrite this as an exponential function. It tells us 3 raised to the y power, and all of that is equal to 1. So now that gives us something that's a lot more easy to interpret. What value of y would you have to choose such that 3 raised to the y is equal to 1? And the answer is y is 0. Anything raised to the 0 power is 1. So this would be the non-calculator way of doing this, if you were to do it as such. So let's go ahead and look at problem 2 over here. So problem 2, we'll look at both ways. We'll start off with the initial way by using the calculator. But to use the calculator, we have to write it in the correct form. So the formula that I imposed up here, this says we evaluate log of 49 and divide that by log of the square root of 7. So it's log of the bigger number, the number straight across, divided by log of the square root of 7. This would be the calculator-friendly version. So you will have to have log, open parentheses, you will have to put in the square root of 7, close 2 parentheses. If you plug all of this in your calculator, you're going to end up getting 4. You will end up getting 4 from the calculator, and that would be correct here. Additionally, if you wanted to use another method, we can again use this idea of imposing a y. And with this, we can again use that loop method, the windmill method, and rewrite this into something that is more easily interpretable. So here, that tells us that we can reformulate this as the square root of 7 raised to the y is equal to 49. And then the question is, what power of the square root of 7 do we have to take to get 49? Well, it turns out the answer will be 4. So if you prefer to use this method, that would be the procedure in which you do so here. And let's go ahead and move on to the final one. So notice, we don't have to use this conversion here. I provided this conversion, or this equality here, to help you be able to interpret the log or put the log in the calculator. But the natural log, it doesn't have a subscript, which means all of this can go into your calculator directly. So if you're able to do all of this correctly, you can plug all of this in, just all as one expression in your calculator. One exception, so it also involves the e, so this is a good problem to practice in the calculator. So in the calculator, you would type in the ln button, which will automatically open a parenthesis, and then you would press the square root symbol, and then you will have e, and it will immediately impose what's called a caret. It means it wants a power for e. Now here, e doesn't have a power, so here you can put 1, and then you can close the parenthesis here. It might also open up another parenthesis. Just make sure you put 1 and then close the parenthesis. And what you should get is 1/2. So definitely make sure you practice this. That's probably the most considerable aspect of these types of problems, making sure you can put them in your calculator reasonably. And this is definitely a good problem to practice with that. Now, the way of not doing that in the calculator, Here, we would have to rewrite natural log as log base e. Just like this. And from here, we would have to use that loop method, the windmill method. And we get e to the y is equal to the square root of e. So what power corresponds to the square root? Well, that's 1/2. So that would be both ways, both with the assistance of the calculator, even though it says don't use one, I'm saying it's okay. So with a calculator and without a calculator, that would be how you do these types of problems. So next we're going to look at determining the domain of logarithmic expressions. So if you recall from the parent function that I listed as well as the domain is not all real numbers. There is a restriction on the x values you can choose, and loosely, this is because you cannot take the logarithm of 0 or a negative number. So if you take out your calculator and you press log of 0, it's going to say domain error. If you try to press log of -1, it will also say domain error. So as such, the logarithm, as well as the natural logarithm by consequence, require only positive numbers. They're only allowed to input positive numbers, and if not, there is a domain issue. So that's actually something I summarized here. You'll also see it in your notes. The domain of the log base a of some expression m, so m could be anything, as we'll find out in these two problems. So I'm giving another criteria, similar to if you see a fraction, you find the domain by setting the denominator not equal to 0. If you see a square root, you set the radicand greater than or equal to 0. So those were criteria that I gave you. Similarly, this is a new criteria I'm providing for the domain. This criteria is whatever log is evaluating, you set that strictly greater than 0, and you solve for x. So let's go ahead and apply that to these two problems here. So we'll start off with log base 2 of x plus 1. And so the criteria over here says whatever the logarithm is applying, it's applying exactly the x plus 1. And so what this criteria says, you take what the logarithm's applying and you set that greater than 0 and solve for x. So now we have a pretty manageable inequality here. So notice that 2 doesn't matter at all. As we'll notice in the next problem, that 8 is not going to matter. And we'll talk about how the 3 and the -5 come into play. So over here, we set everything the log is evaluating greater than 0. We solve for x. That's pretty simple here. So this would be the answer because we did solve for x. However, the problem wants us to put this in interval notation, which means we need to have, well, the parentheses and brackets. The problem requests we put the answer in that format. So this here in interval notation, so x is greater than this number, so that goes towards positive infinity. It always goes on the right. Infinity always gets a parenthesis. -1's on the other side. And we use a parenthesis as well, because this is strictly greater than. There's no equal to component. If there's equal to, we put a bracket. But actually, this would be the answer for this problem. That's it. That's all we have to do for this. So let's go ahead and look at probably the most challenging domain-based problem, at least aesthetically. So over here. So this problem is complex in the sense that, well, it throws in a whole bunch of extra numbers. However, these numbers don't matter other than what the logarithm is evaluating. So is this 3 within the logarithm? No. So it doesn't matter when it comes to the domain. What about the -5? Is that in the logarithm? No, it's not. So we ignore it. The 8 here, by definition, we ignore the subscript. All we care about is what the logarithm is evaluating. So from all of this, we're taking what the logarithm is in fact evaluating and setting that greater than 0, like what the criteria up here tells us. And from here, it's just a matter of solving for x. So I see a denominator. I'm going to apply the least common denominator real quick. Seems like times 5, times 5, times 5. And from here, we simply get x minus 40 is greater than 0. Of course, 0 because 0 times 5 is 0. And so from here, it's just as simple as solving for x. So we get that x is greater than 40, but very similar to this problem, we want to express this in interval notation. So, same idea. It's 40 on the left with a parenthesis, because this is strictly greater than, all the way to positive infinity. And this would be our answer. And that's how you would do these domain-based problems for logarithms. So now we're going to utilize the parent function of a logarithm to match a graph to the corresponding function, given a choice of, in this problem, 8 particular functions. And so, as I mentioned before, this is a parent function. This is a function shape that you need to know, as well as with the corresponding characteristics. So if the test comes up and asks you to graph a logarithmic-based problem, then you need to know the shape and whatnot. And so you may notice the difference here between the two shapes, or between the two graphs, is that the asymptote, well, one thing to notice, the asymptote is shifted to the right by 1. And you can actually use that to determine the graph straight away. There's another way you can do it though, and we'll actually use that idea a little bit later. But also notice that the shape is the exact same. It's just everything is shifted to the right one time. And as such, that means since the shape is the same, that means there's no reflections. And because there's no reflections, that means any problem that has a negative sign in front of the x or in front of the whole function, we can get rid of. And so that actually will eliminate a lot of these answer choices. So let's go ahead and go through these one by one and get rid of all the ones that have a negative in front of an x variable or in front of the whole function itself. So A seems to be okay. So I'll go ahead and write down A. So A is okay. B seems fine as well. C, however, well, C has a negative sign in front of the function, so C is out. D has a negative in front of the x variable, so D is out. E has a negative in front of the x variable. F actually has a negative in front of the whole function. It's just not written in a way that you would immediately suspect it. But since the negative is in front of the logarithm part, that's deterministic, and we can get rid of it. G has negatives in both in front of the function and in front of the variable, and it seems like H is actually okay. So from here, yeah, and I'm in particular not putting parentheses around this. It's log base 2 of x, that whole logarithm minus 1. So that's definitely a clear distinction from part B over here. And so From this, we can actually use a process that we used in the previous section by identifying a test point that we can plug into the x values and see if the function agrees with that. So there is a point on the graph that's deterministic, this point being 2, 0. It's a little bit easier to see on the graph in the notes. But with that, that gives us a test point that we can utilize here. If we plug in 2 for x, we better get 0 for y. So let's go ahead and start with that. So if we plug in 2 for x, so that would be log base 2 of 2 minus 1. But how do you evaluate this? Well, we know how to evaluate logarithms in the calculator. I mentioned this earlier. So this is a good application of that. So it's log of the bigger number divided by log of the subscript or the base. And if you throw all of this in your calculator, you're going to get 0. So this does agree with our test point. So far this is okay. It doesn't mean it's the correct function, but it means we don't eliminate it quite yet. So part B, same idea. We plug in 2 for x and we see if we get 0 for y or not. So we have log base 2 of parentheses, that would be 2 minus 1, which is log base 2 of 1. And we know how to write this in a calculator-friendly version. And you end up, you get 0 again. So you actually do get another function that also agrees with that point. And we'll figure out how to deal with that later. Let's move on to h here. So same idea, plug in 2, see if we get 0 for y. So it's log base 2 of 2, the calculator-friendly version. Just log of 2 divided by log of 2, which is actually 1. But we were supposed to get 0. So if anything, that tells us h is out. So we can eliminate h. And that leaves us with a and b. So we haven't had the situation yet. And so it might be hard to discover another test point because, at least for this problem, they do not have grid lines. Or at least my copy doesn't have grid lines. So as such, if you don't have any other test points to utilize, then we can actually use something I alluded to earlier. The comparison of these two graphs is that this graph is this graph, but shifted to the right one. So do you remember your transformations? What does it mean to move to the right one? Does the number have to be immediately next to the x variable or not? If it turns out to go left and right, the number has to be right next to the x variable. And guess which one of these does that? Answer choice B here. So you could have identified this from the beginning and also chose the correct graph just by this characteristic alone. But this tells us, since we have x minus 1 all happening right next to each other, the minus 1 tells you to go to the right one, which is why the asymptote goes to the right one. A here, since the minus is on the outside, that tells us we would go down 1. Down 1 would not change the location of the asymptote. So A would be out, and B would be the correct answer choice for this problem. So we'll go ahead and look at two problems back to back. They're very similar, and these are virtually bringing together all the ideas we've talked about really in the past 3 sections, as you'll see. We start off with a function for example 6, and this function is remember that means natural log of x plus 4, and the problem just wants us to state a whole bunch of various characteristics about it. So it starts off by asking for the domain, and so the domain of any logarithm, remember the natural logarithm is a logarithm. So how do you find the domain of a logarithm? You set everything that the logarithm is evaluating. So in this case, x plus 4, you take the x plus 4 there, and you set that greater than 0, and you have to solve for x. So when we solve for x, it's just as simple as moving the 4 over, and so we get x is greater than negative 4. And remember, by the principle I established earlier, it's always a strict greater than sign. However, the problem wants us to express this in interval notation. So we have to go one step further. Remember, x is greater than, which means it goes towards positive infinity, which always has a parenthesis. On the left, or the lowest value, that's the negative 4, which also gets a parenthesis by virtue of lacking an equal to component. So we can conclude that the domain is in fact negative 4 comma infinity. So then part B wants us to graph this expression, this function. And so the way we graph it, we have to remember, well, it uses the idea of transformations, which means we need to know what a natural log or a logarithmic function is shaped like, and then know how to transform it appropriately. So on the homework, you'll have multiple choice. It may help to know the construction behind it, but remember the shape of a logarithm in general, it's that shape that, you'll see it on the first page of the notes. It's this shape with an asymptote like this, at x is equal to 0. The only difference is, well, whether it's a logarithm or a natural logarithm, it's not going to change the shape at all, because the natural log is just a special type of logarithm, so it still has that shape. However, the only thing that changes is we look at the graph and we see, are there any reflections? Are there any points where we shift? And it turns out we do have a shift. There's a plus 4 here. So what does a plus 4 mean? A plus 4 applied to the x directly means that we would go to the left 4. So that means we would take this shape and, as you would imagine, shift it to the left 4. So instead of an asymptote on the y-axis, just like how the parent function has it constructed, we're going to shift all that information to the left 4. So we'll go ahead and do that. 1, 2, 3, 4. Now here's where the asymptote would go. And we simply recreate the shape. Just like that. And if you may notice, there is a point on the original parent function. That point is 1, 0, which represents the x-intercept. But since we go to the left 4, that point now becomes negative 3, 0. Because it was 1, 0, we go to the left 4, so then 1 drops down to negative 3. Again, you don't have to know, at least for the homework, you don't need to know this construction that well. It'll be multiple choice, but for the test, it might be helpful to know that tidbit of information. Notice all of that came from the initial parent function, which is why it's important to know this. From here, well, one of the reasons why it's good to know the graph is because we can figure out the range given the graph really easily. Well, how far down does the graph go? We hit an arrow. So if anything, we have negative infinity in that regard. And then going up, it seems as though we hit another arrow, which is fine. We hit an arrow going up, no barriers, so that tells us positive infinity, which this is fairly characteristic for logarithmic functions. Normally their domain is not always perfect, but the range of all logarithmic functions ends up being all real numbers. And here it wants us to also jot down the vertical asymptote. X equals blank, and even in the problem they have x equals for you. They just want to know where this asymptote shifted to. And if you simply count, 1, 2, 3, -4. So that makes sense because the vertical asymptote was at 0, but we shifted to the left 4. So it makes sense that the vertical asymptote is now at -4. And now we're going to find the inverse. We haven't touched this in a while. So remember, what does it mean to be an inverse? This goes back to the last section we talked about before test 3. So for an inverse, you may need to go back and refer to your notes. To find an inverse, you need to switch x and y and solve for y. So when I say switch x and y, so here's the original function over here. F of x is considered y, and of course x is x. I'm going to swap those. So now f of x, which is y, we're going to switch that to x. And then set x equal to natural log of now y plus 4. So this is us merely switching x and y. That's the first step in any algebraic inverse problem. So once we do that, then the goal is we have to get y by itself, because notice, we swapped x and y, now y is no longer by itself, so we now need to get y by itself. So how do we get y by itself? Well, what we need to do is rewrite this expression from a logarithm to an exponential. And that way we can interpret the problem a little bit better. It might give us more of an idea of how to handle this. So what we could do is represent the natural log. So remember that windmill or that loop method I was talking about? We want to utilize that here. But we can't utilize that here because in order for that method to work, we need a log with a base. Notice there's no base here. Natural log doesn't have a base. But we have to rewrite it. Remember what natural log means. It means log base e. So that means the same exact thing. And there's only one reason why we did that, is so now we can use that windmill method or that loop method that I mentioned. And so you might also notice that the functions are on the opposite sides of the equation. Normally when we do the windmill method, you would circle, let me do this in a different color. Normally you would circle the e here and you would loop around and point here. But that's provided you have an equal to part over here. Just aesthetically, the form is not in one we're used to. So instead, it might help to erase that for now. So what I'm going to do is simply switch the sides. So notice what I did. From here, I rewrote natural log as log base e. They mean the same exact thing. And additionally, I just swapped the sides. Now this is on the left side, x is on the right side. This is just all stylistic. And the reason why that's important is because now I have a subscript that I can circle. I didn't have that before. And now I have a way of organizing all of this. Try that again. There we go. So just like that. And now that emphasizes how the exponential function will look. That tells us we start off with e, we raise that to the x power, and all of that is equal to what the arrow is, well, pointing to, y plus 4. And so finally, so remember, we did all of this to try and get y by itself. Y isn't by itself yet though. There's the plus 4. So all we have to do is subtract 4 on both sides and we're done. So let's put that here. We subtract 4 on both sides, y is now by itself, so we're done. That's how you find the inverse algebraically. You switch x and y, and you solve for y, which is exactly what we did. We're also going to go ahead and figure out the domain and the range of the inverse. But it turns out, so this is going back again to what we talked about in the section on inverses. Now when you find an inverse, you're really switching, well, you're switching x and y, but when you switch x and y, that actually has a huge consequence to it. This is something I talked about in that section on inverses. When you switch x and y, it also means you switch the domain and the range. So what you will notice in part F of this problem, it wants you to find the domain and range of the inverse. The domain of the inverse, since you swapped x and y, is the range of the original function. So you don't have to do anything here. The domain of the inverse is the range of the original. That's exactly it. Nothing more or less. So the domain of the inverse, again, is the range of the original. And I have that in the notes for the inverse section. The range of the inverse is the domain of the original. Just notice the domain and range, they just swap. That's all you have to do. So that's all you have to do. Just swap the domain and range. Domain was -4 infinity and negative infinity, positive infinity. Those switched, and that's it. And finally, what we're going to go ahead and do, I'll try and fit the graph of the inverse over here. So remember, the inverse function, I'll go ahead and jot it down. This is what we found in part E, and the final part of this problem wants us to graph this whole thing. And again, it's going to give you a multiple choice. So you don't have to know it, at least for the homework, this intricately. It may be helpful for the test, though, to know how to construct a graph. And so this is an exponential function because there's an exponent. And if you look back to the section on exponential functions, you know that the shape goes upwards like that with an asymptote here. It's got a shape like this with an asymptote at y equals 0. You may notice, though, that the range that we determined for the inverse is -4, infinity, which means that, in other words, this function is being shifted down by 4. So what we can do, well, we interpret it exactly as such. This shifts down by 4. And finally, we can just recreate the shape because there's no transformations of any sort. And there is a point that goes through here. Oops. There is that point. And this point makes sense because this graph is the inverse of this graph. And notice we're just simply switching x and y. That's why it's so important to identify two inverses of one another. But other than that, this would probably be the most complex problem on this homework set, in my opinion, and that's why we're going to do another one right after this one. Alright, so we'll go ahead and look at another one similar to the last one. And so we just have a different logarithmic function, but the same idea. Find the domain, graph, range, inverse, all that stuff. So we're going to start off with finding the domain of this logarithmic function. And remember, the domain of a logarithm, you find the part that the logarithm is evaluating, and you set just that greater than 0. So the 4 here is not in the logarithm, so we don't include the 4. The 3 is the base of the log. Again, the log is not evaluating 3. The 3 is the base of the log though. So instead, the only stuff that the logarithm is evaluating is the x minus 4. So the x minus 4 is what we set strictly greater than 0. And for logarithms, it's always strict greater than. And we solve for x, because that's what the domain criteria tells us to do. And once we set that and get x by itself, well, we get the answer, but we have to put this in interval notation, which is simply 4 to infinity, where 4 has a parenthesis because there's no equal to component. So next, what we're going to do is figure out the graph of this function over here. And as a reminder, the shape of any logarithm. So again, you can reference it at the beginning of the section. It was roughly this type of shape here with an asymptote at x is equal to 0. So we're going to be conforming to this shape in one way or another. So now we need to see what happens to the shape based off of transformations. And so this shape's always going to happen regardless of which base we have for the log. So here we have, well, 2 different types of shifting. We have a 4 plus and an x minus 4. Now, again, that goes back to the how transformations come into play. So if we have a number directly affecting the x, then that tells us we're going left or right in the opposite direction. So this would tell us, well, minus 4, we have to do the opposite. It's to the right 4. And then this over here, so this one would be up and down because it's outside of affecting the x. So this one tells us up 4. And so once we figure out all of that information, that's how everything here will be translated. So we could take our graph here. The asymptote here, this vertical asymptote, only changes if we go left or right. Only go left or right. If we go up or down, notice the asymptote still stays as is. So only left or right will affect the asymptote on the graph. So we're going to the right 4, so that vertical asymptote would go to the right 4. So let's go ahead and resemble that, if anything. 1, 2, 3, 4. So we have an asymptote there. If we go up 4, then this vertical asymptote is still there. And so the only thing that will change, so remember, the parent function of a logarithm, so if we were to check out the graph of a logarithm, then, and again, this is resembled on the parent function at the beginning of the notes for the section, there is a point that you get. So a way we can slowly approximate this graph to something a little bit more exact is by seeing how the shifting would affect that point, that given. And so if we go to the right 4, that tells us this point goes to the right 4. So instead of 1, 0, that would be 5, 0. But we also go up 4. So instead of going to the right just 4, we go to the right 4, up 4. This would now become 5, 4. So 5, comma, 1, 2, 3, 4. And that tells us a definitive point for which the logarithmic function will go through. So in essence, what this shifting does is it tells us where the arc might happen at. I don't think my illustration here does it justice, but it does shift that part of where it starts to level out, shifts that upwards, as we have here. The point guides us in that particular location of where that happens. And so for reference, that point is 5, comma, 4. We go to the right 4, which turns the 1 to a 5, and we go up 4, which turns the 0 here to a 4. And so from here, as we did in the previous problem, we're going to determine the range of the vertical asymptote, since we now have the graph available to us. The range, well, the range for all logarithmic functions is all real numbers. And you can also tell that by the graph. It goes down forever, it goes up forever, because there's no horizontal asymptotes restricting us from going up or down. The vertical asymptote, it just wants to know where this vertical dotted line shifted to. And if we just count 1, 2, 3, 4, that tells us that the vertical asymptote is at x is equal to 4. And so now that we have that, we can go ahead and determine the inverse function. So again, what does it mean to be an inverse? How do you find an inverse algebraically? Again, you have to switch x and y and solve for y. This is in the inverse section. What I just said, that's there if you need to reference it. So once we switch y for x, I'll go ahead and write this in red. And then we jot down everything else, but we're going to replace x with y. So now this is exactly what we have. And we have to get y by itself. Now, I want to utilize that loop method, the windmill method, which allows us to turn logarithmic functions into exponential ones. However, there's one thing we have to, well, there's a few things we have to modify. For the windmill method to work, and we haven't seen this, so far in these examples, we haven't seen a situation of this yet. For the windmill method to work, the logarithm needs to be by itself. This is very similar to when we did the section on radical functions, and you had to get the square root function or the third root function, fourth root function by itself before you raise both sides to a particular power. It's the same idea here. So in other words, what that boils down to, we need to move the 4 over here right fast. So let's go ahead and do that. So now the logarithm is by itself. But for the windmill method, we're used to the equal sign being on the right of the logarithm. Again, you can always make the windmill go this way, but if you like consistency, then make sure your logarithm is 1 by itself and 2 on the left-hand side of the equal sign. So I'm just going to swap the two, like I did in the previous problem. So all I did was just swap them. So it's good to have the logarithm by itself, and it's good to have the logarithm on the left-hand side. And the reason why I make it as such is because it follows the conversion, this mnemonic way of translating all of this into an exponential function. It organizes it very well for us. And so this would be 3 raised to the x minus 4 is equal to y minus 4. So our exponent has more than one term in it. And that's okay, that happens. So it's 3 raised to the x minus 4. So x minus 4 is the exponent. And all of that is equal to what the arrow is pointing to, which is more than one term. And that's okay, that happens. But remember, we're trying to get y by itself. There's only one thing getting in the way of that, and that's just the minus 4. So we have to bump the negative 4 to the left to get y by itself. And once you get y by itself, then that tells you the inverse. And if it's hard to see it down here, I'll try and write it up here. So this would be the answer. Once you get y by itself, that would tell you the inverse function of the original function. And again, why is it so important to know the inverse? Well, once you know that these two are inverses, then you get the domain and the range for free. It's just everything's swapped. Everything we've looked at is swapped. So the domain of the inverse is the range of the original. Remember, everything's swapped. That's what it means to be an inverse. So the domain here is the range of the original. The range here is the domain of the original. That's it. So with an inverse function, you get all of those for free. It's just everything is switched. And then the graph, so we're trying to figure out the graph of 3 raised to the x minus 4 plus 4. So if you can identify how transformations will affect this. So this is an exponential function. We know that the shape is looking similar to this shape here. This would be in the last section, the parent function, with an asymptote here. Well, the transformations here, the shifting here, that tells us right 4, because remember it's the opposite when we're going left or right, and up 4 when it's not affecting the x directly. The horizontal asymptote will only change if we're going up or down, because left or right still just goes infinitely in both directions. So this horizontal asymptote shifts up 1, 2, 3, 4. We know one point on the exponential for free. This one is 0, 1. If you look at the parent function, you'll see that it does give you a y-intercept for free. So this y-intercept goes to the right 4, so then 0 shifts to 4. And then up 4 means that the y value goes to 5. And then that helps us trace the graph accordingly. It pretty much tells us when we start to ascend towards positive infinity. And again, this might be helpful. This might be helpful for the test if you're asked to construct either a logarithmic function, an exponential function, or there might even be a problem like this where they ask you to do both. But other than that, that would conclude this problem. So now we're going to go ahead and solve some equations involving logarithms. So this will ultimately utilize the conversions from logarithmic expressions to exponential, or I guess statements as they call them. So what we're going to go ahead and do, we'll start off with problem 1 here. And whenever we're trying to, if you're at a log-based problem and you're trying to solve it, which means we will try to get x by itself, One thing you can always try to do is rewrite from a logarithmic expression to an exponential one. And the way we can do that is by using that loop windmill method. So remember, there was kind of two rules of thumb that I mentioned. You want the logarithm on the left-hand side, and you want the logarithm to be by itself. Well, it turns out for this problem, and actually for all the problems for these next four, they do give us that convenience. So we don't have to do anything else other than directly apply that method that I just mentioned. So this tells us 2, we are rewriting this as an exponential. 2 raised to the second power is equal to, well, 8x plus 4. And notice that conversion simplifies this into something that's really easy to solve. That's why this is such a natural idea to consider. And of course, 2 squared is 4. You go ahead and solve, you subtract 4 on both sides, and ultimately you will get that x is equal to 0. You'll subtract the 4 on both sides, you get 0, you divide by 8, 0 divided by 8 is 0. So this would actually be your answer for the first part here. Let's go ahead and move on to part 2. And notice, before, the x was what the logarithm was evaluating. Now the x is the base. And well, despite where the location of it's at, if you're unsure of what to do in a log-based problem, you can go ahead and see if you can convert it to an exponential statement. So the logarithm's on the left, it's by itself, so let's go ahead and apply the same process. And that tells us x to the second power is equal to 25. Just like that. And now we can solve from here, which would require us to square root both sides. Which requires a plus or minus. So if you were to try and put this into my math lab, it's going to say that you're incorrect. And you might think, well, what do you mean? We just did all the steps and we get plus or minus. The issue comes into play that logarithms cannot have, so not only can logs not evaluate 0 and negative numbers, you cannot have a base that is a 0 or a negative number. Your base always has to be greater than 0. It has to be a positive number. Remember, x represents the base, so x has to be a positive number. That's why the -5 doesn't work in this situation. So all we have is x is equal to 5, because when x is equal to -5, we have a negative base, and we cannot have a negative base or negative subscript of a logarithm. So let's go ahead and move on to problem 3 here. So for problem 3, again, it's already written in the familiar form. Log is on the left, and log is by itself. So again, we can apply that windmill method, or there's actually 2 ways you can do this. And I'll go ahead and separate the 2 ways. So you can use the windmill method on one hand, and you would get an expression like this, which then you ask yourself, okay, 6 raised to what power gives you 216? And I'm pretty sure that is 3. So here we get 3. You can also, if you have a logarithm that has all numbers, so we haven't had this yet. If we have a logarithm that has all numbers, then we can actually put it straight in the calculator. So over here, We have x is equal to log base 6 of 216. But remember what I mentioned a few problems back. This can be rewritten as log of what you are evaluating divided by log of your base. And this is the calculator-friendly version of what we were just trying to figure out. And so if you put this in your calculator, you will get 3. So either way, you get 3 as an answer. This is 2 ways you can do the problem. And this is whenever you have all numbers. Over here you had an x, so you didn't have that luxury. And so we'll go ahead and move on to problem 4. So problem 4 seems to be the most difficult one here. So notice we cannot plug all of this in the calculator because there's an x there. So that x is actually a part of the 49. So this logarithm that we're looking at, it's evaluating log base 7 of 49 raised to the x. So whenever we use the windmill method, we have to make sure that the 49 raised to the x, that's all together. So that's 7, quantity raised to the quantity -2 is equal to 49 raised to the x. And from here, now we have an exponential is equal to an exponential. Well, that reminds me of something we talked about in the previous section. If we have some sort of equality like this, we can try and get like bases. So let's see, how can we turn one of these to become the other base? We can rewrite 49 as 7 squared. So let's go ahead and do that. So 49 is 7 squared. And now we have an exponential raised to an exponent. So try and remember your law of exponents from the previous section, because they come back here in this problem. If we have an exponent raised to an exponent, you multiply these exponents. So 2 times x is, well, simply 2x. From here, since we have like bases now, they cancel. And you get -2 is equal to 2x. Or in other words, x is just -1. When you divide 2 on both sides. And that would conclude example 8. So now what we're going to do is, instead of looking at logarithmic equations and rewriting them as exponentials and solving, we're going to go in the opposite direction. We're going to consider exponential equations like these two presented here and try to rewrite those as logarithms to see if we can have any success in getting an x by itself and, well, solving the equation. So we'll go ahead and start off with problem number 1 over here. And so what we want to do, so generally rewriting an exponential to a logarithm is a good idea whenever you have the variable stuck in the exponent. Notice there's a variable stuck in the exponent. And again, stuck in the exponent over here. So what we're going to do, so remember, I'll go ahead and write down this rule as well. Oops, not 2. So the rule is, if you have some exponential function, you can rewrite it like this. So this was a rule I mentioned before. We don't necessarily have a mnemonic way of transitioning like we do in this direction, or if you have one, then you can definitely use it. So I'm going to make sure that I translate everything appropriately. So one of the easier parts is knowing that the base of the exponent is legitimately translated as the base of the logarithm. So to go from here to the log, we have log base e. Base of the exponent is the base of the logarithm. And then what do we do next? So the next number is going to be, well, what the whole exponential is equal to. Here it's x, and then x ends up going to be what the logarithm is evaluating. So here, the 3 is what I put. And then all this is equal to, well, whatever the exponent was. That is the 2x plus 7. Now something that's interesting to notice here, so this problem actually says, so in my notes I say the common log. I think in the homework it actually says express it as a natural log. And we can do that here because we have log base e. And guess what log base e is? We have a shorthand for it. It's ln. So if it says express as a natural log, then that's it. They just want you to use, they're just telling you what notation to use. Remember, by definition, these mean the same exact thing. It's just a shorthand. But we're still trying to get x by itself. So to get x by itself over here, we have to subtract 7 on both sides. We'll start. And notice ln of 3, you could technically evaluate that in your calculator, but you get a weird decimal, 1.098. The problem wants you to put an exact answer. It does not want you to simplify any of this. It does not want you to get a decimal. It just says, you have this messy number, just leave it, just let it linger around. As we'll see more so when we get x by itself by dividing 2 on both sides. So finally what we have is exactly this. And a common mistake I see from students, sometimes they'll say subtract the 7, and they'll put the 7 in the parentheses, or they'll subtract 3 minus 7. You cannot do that. If a number is in a log or a natural log, outside numbers cannot affect it. So we do not have 3 minus 7 here. That is not the case. That actually breaks order of operations. It's natural log of 3 minus 7. At no point do we subtract 3 minus 7. Same with divide by 2. We don't divide 3 divided by 2 here, and that number just end up in the natural log or any logarithm. So those are common mistakes I see students do, and try to keep in mind if a number is trapped in a log, outside numbers cannot affect it. So keep that in mind. And we'll go ahead and move on to problem 2 here. And this one's probably the intricate of the exponent to logarithm based problems. And that's because, well, they throw in this additional 2 times. So they throw in this, and so this form as it stands actually does not conform to the initial form for which we can translate. That 2 is just getting in the way. And so the only thing we have to do, so this is actually very similar to the idea I mentioned earlier about we need logarithms to be isolated. We also need exponents to be isolated. 10 raised to the 9 minus x is the exponent, and 2 is getting in the way. So we have to divide both sides by 2. So by doing that, now we have a raised to some power is equal to some number. And now it's in the format that we can utilize. So to convert this to a logarithm, so it's going to be log base 10. Remember, the base of the exponent is the base of the logarithm. This is going to be log base 10 of the number over here, as the formula states. And that is equal to the exponent, 9 minus x. So now that we're here, and also, as I mentioned before, if you ever have log base 10, you technically don't have to write the 10. If there's no subscript here for a logarithm, it's understood to be 10, but from my experience, if you leave the 10, it won't count it wrong, but I'm just letting you know. And so we still have to get x by itself. So we can go ahead and, well, subtract 9 on both sides. So let's go ahead and do that. So all I did was bump the 9 over here by subtraction. And again, the 13 over 2 and the 9 do not go together. The 13 over 2 is within the logarithm. The minus 9 is not, nor will it be. But we still got to get x by itself. There's the negative in the way, so we multiply or divide everything by negative 1, which is going to flip all the signs. And finally, what we end up getting is that x is 9 minus log base 10, or subscript 10, of 13 over 2. And it does want an exact answer. So this would be your answer, very similarly to how this would be your answer as well. And this problem says to express it as a common log, not a natural log. So this answer format would be okay. But other than that, this would be the basis for exponential functions to logarithmic functions. Finally, we'll go ahead and take a look at one of the application problems at the end of the section. So for this one, we start off with a function, a logarithmic function, and what I'm going to do before we even start, pH, I'm not really too, I guess, I don't want everyone to get hung up on the notation, so we're going to call that f of x, and this bracket, I'm guessing hydrogen ion, whatever they call it, I'm just going to call it x. So here we already just went ahead and translated pH to y and h plus to x. So for parts A, B, and C, when it says h plus, it says what is pH when h is some other thing. What that translates to is when x, what happens when x is 0.1 and it goes on in a similar fashion. So that's what we're going to go ahead and do, and we'll do that to this function here. It'll just make things a little bit easier. But this says ultimately plug in 0.1 for x and solve for y. So let's go ahead and start doing that. So negative log base 10 of x, but x is now 0.1. So we want to evaluate this, but how do we evaluate a logarithm? We have to write it in the calculator-friendly version. So just like this. So notice the negative sign just carries over, and the logarithm stuff follows that formula that I talked about before. And so if you plug all of this in your calculator, so there's a negative in front, so I'll go ahead and leave the negative. Log of 0.1 divided by log of 10, you should get negative 1 from that. So log of 0.1 divided by log of 10, and you get negative 1. And that's in addition to the negative that was already out here. So all I did was plug in the fraction. Or you could plug it in all at once and you'll get positive 1. And in any case, you should get 1 as your answer. So let's move on to part B here. It's the same idea, except instead of x is 0.1, well, we're going to plug in x is 0.01. So let's go ahead and do that as well. But it, of course, follows the same idea. all of that correctly, you should get positive 2 as your answer for that one. And then finally, same thing, but just they append another 0 to the front. This one you will get 3. So make sure you're comfortable with plugging and evaluating logarithms in your calculator. But once you get all of those 3, well, there's still 3 more parts to this problem. And so actually part D, what that asks is whenever the hydrogen ion concentration, remember we said the hydrogen stuff is X. So it says whenever your X value decreases, as it's been doing here, here, and here, what happens to the Y value or the pH value? So notice it goes from 1 to 2 to 3. Seems like it increases to me. So for part D, you would just say that pH increases because it's saying when the X value decreases, what happens to the Y value? Simply increases, as we see here, just gets a little bit larger each time. So from there, we'll go ahead and move on to parts E and F. And so what E and F both want us to find, well, what they're doing is giving us pH is equal to 32. So we'll start with E. So 3.2. But remember, we said that pH is now Y. So they're giving us Y is equal to 3.2 over here. And they want us to find the hydrogen ions, they want us to find X. So if we plug 3.2 in for Y, we get exactly this equation right here. And that means we need to, well, solve for X. But how do we get X by itself? Well, this is when that windmill or that loop method comes into play. This is when the conversion to an exponential form helps. But remember, 2 rules of thumb, neither of which are satisfied right now. One of them is the logarithm needs to be by itself. It may look like this, but that negative sign is getting in the way. So if anything, we need to go ahead and multiply both sides by -1. So if anything, the logarithm is now by itself, it's now isolated. The other rule of thumb, which helps with our kind of mnemonic way of converting, is the log needs to be on the left side. So let's just go ahead and swap the 2. So that's all I did. I just swapped which one was on the left side, which one was on the right side. And from there, that's helpful because we can immediately follow that loop method, which tells us how to convert this to an exponential function. It says now we have 10 raised to the -3.2. That's all equal to X. Well, look at that. We have X by itself now. And the problem wants us to approximate this to 6 decimal places. So it doesn't want an exact answer, it wants a decimal approximation. So if you were to put this quantity in your calculator, 10 raised to the -3.2, so 6 decimal places, 0, 0, 0, 6, 3, 1. And that would be the answer you provide for part E. And part F is going to be fairly similar. In fact, part F is in fact so similar, I'm going to leave a lot of this here. So part F does is simply change 3.2 to 7.8. It follows the same exact idea, so every 3.2 that I see, and you can derive all this yourself if you'd like. And then finally, this one right here. So if you follow those same exact steps, you will get exactly right here. So then that'll of course change the value here. So what happens when we plug in 10 raised to the negative 7.8? So I see a whole bunch of zeros and a 1/6 at the end. If you look at this problem in the homework though, it'll have an answer choice, or 4 possible choices. They're all going to be in scientific notation. So this is the only problem like this, and that's why I want to tell everybody about this. So if you press second, so what I'm recommending is putting your calculator real briefly in scientific notation. If you press second and the button directly to the right of second, it'll pop up a screen that says flow, psi, and eng. Go ahead and move your cursor, enter on psi, and you will get actually the answer. You will recognize one of the answer choices. It will be 1.584, how many? And in fact, they'll just have it to 3. You will definitely recognize the answer choice in comparison to the other ones. And if you want to convert your calculator, or in fact I would suggest after you're done with this problem, convert your calculator back to the original form. So you could press second, you could press the psi, English, or eng button, and go back to flow, which just means floating point. And you should see the zeros and the 16. So other than that, this would be your answer for this problem. So a little bit complicated in terms of finagling around with getting that exact answer. But other than that, that actually concludes the section on logarithmic functions.